Let us recall what we have done in the previous lecture. So in the previous lecture, we have discussed this property that any function you have given, which will have finitely many discontinuity, jump discontinuity in the interval 0 to 1, then you can able to express this function into the series of Bessel's function, that is summation n running from 0 to infinity, sorry, 1 to infinity, an jp lambda n x, where lambda n is the zero of Bessel's function, and where you can be able to calculate this an as 2 by jp plus 1 lambda n square integration from 0 to 1 x into fx jp lambda n x dx. So with the this things, also we can recall what will be the Jacob this Bessel's function is. So the Bessel's function, we know that it is jp of x is summation n running from 0 to infinity minus 1 raised to n upon n factorial into p plus n factorial into x by 2 power 2n plus p. Then this Jacobian is also, or this Bessel's function is also can be written, if I change this index with k, then it is also can be written as, which is also same as, I can say, a summation running from k to 0, 0 to infinity, minus 1 raised to k upon, so instead of p, I am just writing n here. So that is k factorial into n plus k factorial into x by 2 power 2k plus n. Now with the help of this, we'll discuss the next property, that is known as the Bessel's function of integral order. So that is the next things we have, which says that true that for the Bessel's function, Jn of x of the integral order, where n is an integer that I required. So n is an integer. It is e power x by 2 into t minus 1 upon t. This is all into the power, exponential power, equal to j0 of x plus a summation n running from 1 to infinity jn of x into t power n plus 1 minus t power minus 1 raised to n into t power n. If I can represent this, if you know that recurrence, or we have learned that the relation between this Jacobian with minus n, x will be minus 1 raised to n Bessel's function of that. This relation we already know. If we use this relation here, then this expression also can be written as e power x by 2 t minus 1 upon t is equal to j0 of x plus summation n running from 0 to infinity jn of x into t power n plus summation n running from 0 to infinity j minus n of x t power n, because this minus 1 raised to n into jn of x will be written as j minus n at x. And if you can write down this two summation combinedly, then one can write this as summation n running from minus infinity to plus infinity jn of x t power n. So now we'll to prove this, either you can state in this fashion or in this fashion, both of them is valid, or both of them expressed as the same thing. Now our objective is to prove this theorem. That means this integral order is this. So prove this, we'll use the series expansion of this series, exponential series. So here I'm starting with the LHS side, that is e power x by 2 into t minus 1 upon t. That can be written as e power xt upon 2 into e power minus x by 2t. That I can also can write down as e power xt upon 2 into e power minus x into t power minus 1 upon 2. Now we know that the series of e power x, that is e power x is equal to 1 plus x square by 2 factorial, x cube by 3 factorial, and so on, which we know that it is can represent as summation 0 to infinity x raised to n upon n factorial. If I can write down with the changing this index, then also there will be no problem. So then this LHS, or I can say in this LHS we have e power xt and e power this. So we can write down for both of this. So therefore we can have e power xt upon 2 will be summation j running from 0 to infinity xt by 2 power j upon j factorial, which I can write down that is as 1 upon j factorial x power j upon 2 power j into t power j, and e power minus xt power minus 1 upon 2 also can be written as summation k running from 0 to infinity minus k xt upon 2 minus 1 is here power k upon k factorial, which can be written as summation k running from 0 to infinity minus 1 raised to k upon k factorial x power k upon 2 power k into t power minus k. Now, in order to get this LHS, we have to multiply this to power series. So it is the resulting, it's called the double series. So we have a double series, and to find out this double series, we should use the condition of the positive term in which the consider any one of the term from the first series and from the second series. So we have to use the Cauchy product here to get this product of these two series. To use the Cauchy product, let us write that quantity. Now to find LHS, we formally multiply above two series, then the resulting series is called a double series. and to find every term of a double series, we should consider all positive terms, in which we can consider any one term from the first series and any term from the second series. So let us keep this any fix n greater than or equal to 0, and then we'll find out what is the coefficient of t power n into the double series. To find the coefficient of t power n in this double series, we should take j is equal to n plus k, and all the possible values of k should be counted. Hence, the total coefficient of t power n is the summation k running from 0 to infinity 1 over n plus k factorial x n plus k upon 2 power n plus k to minus 1 raised to k upon k factorial into x power k upon 2 power k. And this is actually what we have is the Jacobian. So this is actually summation k running from 0 to infinity minus 1 power k upon k factorial into n plus k factorial x by 2 power 2k plus n. So this is x power k plus k, that is 2k plus n, and in the denominator also we have this. So this is a Bessel's function at x of order n. Let us keep n fixed, that is n greater than or equal to 1, and to find the coefficient of t power n, we should take k equal to n plus j, and all possible values of j. So the total coefficient of t power minus n is summation j running from 0 to infinity 1 over j factorial x power j upon 2 power j minus 1 raised to n plus j upon n plus j factorial x power n plus j upon 2 power n plus j. So this we can write as minus 1 raised to n summation j running from 0 to infinity minus 1 raised to j upon j factorial into n plus j factorial x by 2 power 2n plus not 2n plus 2j plus n. So that is minus 1 raised to n into jn at x. So hence your LHS is summation n running from 0 to infinity. So what we have is this. LHS is this into this. So when you do the product of these two terms, see here actually what we have used is this summation of an into summation of bn is summation of cn, where summation this cn is the a0 bn plus a1 bn minus 1 up to so on up to an b0 is there. So this is the things we have. This is a known as a Cauchy product. So here the summation, this is your an. So for the positive terms, that means if there are terms which we have, if this is this if you consider this is your an, then there are terms which having the positive powers. That is the power which have the t power something is positive, and there are terms which having the negative powers. Okay, because of this quantity is multiplied with this. So this cn in the short form it can be written as k running from 0 to n, ak b n minus k is there. So when you apply this n minus k, it may possible that there are positive powers of k is there and there are negative powers of k is there. So for the positive powers, we have calculated this t power n, and which is into the similar formula we have this n minus k. So in that case, we have this is the quantity we have, and for the negative powers, we have this n plus j. So that's why, and if we can substitute all these values here into the LHS, so this series expansion of this is power e power xp upon 2 will have this answer, that is jn into t power n, which is a positive powers, and for negative we'll have n running from 1 to infinity minus 1 raised to n into jn x into t power minus n. And if you combine both of them, it will be j0 is you can write down separately plus summation n running from 1 to infinity, jn is common out, you will have t power n plus minus 1 raised to t power minus n. So which is our objective is to prove here it is a minus n, please correction is there is a correction. So that's why I can write down this is into this form. So this is minus 1 is here. No, there is no minus 1. That is perfect. That is correct. No minus 1 is here. It is positive, perfectly right. So if I have this one now, if I replace this n by minus n, if I replace n by minus n here into this series, then we will have that. So that is equal to, so the LHS equal to, we'll have j0 of x equal plus summation n running from 1 to infinity jnx t power n plus summation n running from 1 to infinity j minus n x into t power minus n. And if I replace n by minus n into the second series, we'll have LHS equal to this both things. If I can write down combinedly, that is 0 to infinity j n x t power n, plus this is, I can write down, since I want to replace n by minus n, this will be replaced by minus n, so that is minus infinity to minus 1 j n x into t power n. And if you can write down both this combinedly, that is n running from minus infinity to infinity j n x t power n.
Sir, in the first series, the last term will be minus 1 raised to n jn of x into t raised to minus n. Last term.
Here is minus.
Yes, minus 1 raised to n and j of plus n. It
Huh.
is j of plus n.
But we have used this expression, that is jn of j minus n of x is equal to minus 1 raised to n into jn of x. We can use this relation of Bessel's function.
Okay, sir.
Here it is minus 1 raised to n into jn of x is there. So that if I use this relation, then it will be j minus n of x. So that's for that you will have this. No problem with that. All right. So any other question you have in this?